think we can now move on to Ian Wood, who's going to talk to us about Judith Milledge, not such a well-known figure, but Ian and I have known each other for about 30 years.
Probably.
I first got to know him when he was helping Judith Milledge transfer the Kathleen Lonsdale material to the Science Museum. And after Judith retired, he carried on giving. I remember in particular a time I picked up a densitometer, which was about the size of a large photocopier. And I think that was about the last major donation we made. But anyway, I give you Ian Wood on the subject of Judith.
That's all right. And sorry, could you get this forward? Okay, thanks. Hello. Well, Judith is, I think, one of the least well-known people probably being talked about at this meeting, but I think she's well worthy of being here. Like Helen McGaw, she lived a very long life. She died when she just passed her 94th birthday, only a couple of years ago. What I'm going to tell you about today is a little bit about her life, career, some of her collaborators, and then a few of the things that she was interested in. She had an eclectic career. She was interested in all sorts of different things. So I'll say things briefly about apparatus, computing, in particular on diamonds, teaching, and then some things about her influence on life at University College, which I think has been quite profound in some ways. So she was actually born in South Africa in a small town called Kokstad, which is shown by the red mark on the map there. It's quite near to Kimberley. It's about 300 miles from Kimberley, which is famous, of course, for the diamonds. And I think this probably had an influence on her later life and her later career. She came from a relatively well-to-do family, I think, but had fallen on slightly hard times, and they'd gone out to the empire to kind of seek their future, initially as farmers, but that didn't work out very well. And her father, I think, became the editor of a local newspaper in South Africa. At quite an early age, Judith went to Rhodes University. She would only have been about 16 or 17 at the time. So it was towards just after the end of the war, really. She wasn't sure what to study there, so she talked to the professor of chemistry, who realized that she didn't know very much chemistry, or much science for that matter, and said he thought she'd be much better off studying physics, so she was sure she'd find it far more interesting. So she ended up in the physics department there. And most of the people she was studying with, or a lot of them, were of course South African young servicemen who'd been returning from 4 or 5 years fighting the Germans in North Africa. And it must have been an extraordinary environment for a young woman. There would have been very few women in the university, even fewer studying physics. And here she was with these guys who were all kind of 24, 25 or whatever. And she said they delighted in sort of destroying the laboratory in ever more inventive ways and things, because just joie de vivre and relief to be alive. Anyway, after that, she got a job at De Beers, the diamond company, in their research lab in Johannesburg. And this is a photograph of Judith, age 21. And in case you're amazed at the colour photography in 1921, of course, Mike Glazer very kindly tinted this for us when we wrote the Judith's obituary a year or two ago. Her later life, she came to UCL in 1949 because De Beers recognised that she needed to learn about X-ray crystallography and X-ray diffraction. And really the only person in South Africa who could probably teach her was R.W. James, but he was quite ill at the time. And he said, go to London and study with Kathleen Lonsdale. So she came to work with Kathleen and did a PhD on diamonds, partly paid for by De Beers, and I think partly paid for by providing secretarial help for Kathleen, who was at the time working as editor of the new international tables for X-ray crystallography, as we heard earlier in the talk. After that, she went off to MIT for a year or two and worked with Sid Abrahams at MIT. And then she came back to UCL in the early 1950s, and she stayed at UCL for the rest of her career. Initially, she was in the Department of Chemistry, where she worked with Kathleen. And then she was appointed reader in crystallography, and this was quite important, reader in crystallography at the University of London, not at University College. Now, I pitched up on the scene in the mid-1970s when I did a PhD with Judith. And at the time, the chemistry department was, I think it's fair to say, going through some difficulties. Ron Nyholm had been the head of the department, was killed in a car accident, and there was a lot of division. The department was split between two buildings. It was not perhaps the happiest place, and I think the college didn't make the wisest choice as to their new head of department. And Judith decided that she would seek her future elsewhere at UCL, which she was able to do because her appointment as reader came from the university as a whole, not from the college, and she could hold that readership in any institution of the University of London she chose to do so, and in any department that would have her. So she moved to geology in 1978, and she carried on working there until well into her 80s, and in fact her last paper she was a co-author of was published when she was 87. I should mention a couple of her collaborators in particular. Kathleen Lonsdale, of course, we've heard about today, had a profound effect on Judith's life and career. It carried on long after Kathleen's death. But she worked a great deal with Monica Mendelsohn, who's in the audience here, particularly on diamonds. And another man that I should mention is the chap with the beard and glasses on the back row there is Pete Woods. He was the technician who worked in the group when I was there and later. And Peter, he ran the electron microscope that we had, the scanning electron microscope. He was a fantastic guy. He could build all sorts of apparatus, do photography, wonderful, wonderful person to work with. So, as I said, she was interested in so many things, and I've given a few things about bits of apparatus she was interested in. She was extremely inventive. This, I think, is her second publication in Acta Christ in 1951. And she wants to make a monochromatic divergent beam. And she's come up with this idea that if you can have a spherical cavity in a crystal set such that the Bragg angle is 45 degrees, the beams from the X-ray tube will all converge at the point B on the right-hand diagram and produce this diverging beam. I don't think this device has ever been made, but I guess in principle it could be. Another one that I picked because it's related in many ways to later work done by people like Mike Glaser and Helen McGaw. There's this idea of using a screens on a camera just to select a certain family of spots. Now, you could do this very easily with a Weissenberg camera, of course, but Judith made this device to go on a Unicam S25 oscillation camera, and she's got a set of exposures made under different conditions. And this was a technique that Mike in particular used very beautifully to look at phase transitions in perovskite. Oh, there was one other thing on this. In those days, you got 10 shillings for each paper published in that section of the Journal of Scientific Instruments. I was quite amused by. Something else which I've brought with me is the device on the left there. It's a Gandolfi attachment to fit on one of these S25 oscillation cameras. It effectively lets you take a powder photograph from a single crystal. Why would you want to do that? It can be quite useful in mineralogy if you've got a powder data set from a locality and someone gives you a little crumb of material and said, is this the same stuff? Then using a Gandolfi device can be quite informative. But you can have a look at that later if you want. The first Lonsdale and Milledge paper, as opposed to Lonsdale and Grenville-Wells after Judith was married, has this most wonderful title, A New Use for Old X-ray Tubes. And the mind sort of boggles. It was related to their work on diamond, and they had an old contaminated tube which had copper radiation, which it should have been giving out, tungsten L from the target from the filament being sputtered onto the target, and also nickel lines. I'm not quite sure how the nickel got there, but anyway. But they were able to use this, and they were able to use the differential absorption at different wavelengths to infer that the included material of another mineral inside this diamond must have contained nickel. And it was just a really sort of ingenious use of something that you wouldn't really normally perhaps bother with. The final bit of apparatus, there are many more I could have chosen, was something that she did when she was at MIT. And it was effectively like Beaver's Lips and Strips, but in 2 dimensions. And it was a moving strip Fourier analyzer, letting you calculate Fourier transforms, electron density maps in 2D. And of course, you would have been extremely familiar with Kathleen's work on the Fourier map of hexachlorobenzene, for example. But of course, this is now the 1950s, moving into the 1960s, and digital computers were now coming on the field. And at this point, I've got to mention Judith's involvement with this thing. This is the Ferranti Pegasus computer, which was in UCL when I was doing my PhD still. It arrived in 1964, and it probably originated from a conversation between Kathleen Lonsdale and Judith, where Kathleen said, one of us is going to learn to use a computer, and I do not think it is going to be me. So the Pegasus, after it was retired, it moved off to the Science Museum. The photo on the left shows it in more detail, the two bays. The photo on the right here is a better representation of the colours. The coachwork was by Mulliners, who built Bentleys. It's got a very, very nice analogue clock on the front of it there. And it came, I believe, from Scottish Widows. It was second-hand when they got it. It used valves. Had a 48-bit word, 128 words of primary storage, so that turns up to 700 and something bytes in modern speak. And there was about an 8,000 word magnetic drum that rotated round under the operator's feet at about 4,000 RPM. Or you could store steps in your calculation on 5-hole paper tape, punch them out, and then read them in again later on. There were a couple of oscilloscopes on the front there in which you could see the individual bits. If you didn't like a bit, you could toggle one of the toggle switches and change it from 1 to 0. And it said it was often necessary to use ingenuity to reduce the number of transfers between the fast store and the drum. Now, Judith wasn't the only person to use this computer. That is Mike Glaser as a young man. And I got this fantastic quote from an article Mike wrote. We were very lucky in Lonsdale's research group as we had for our own personal use a real computer. I think we may have been the only scientific research group anywhere with its own computer. That may have been true at the time, of course. Judith did a lot of quite advanced work, I think. She wrote this long paper for Proctor Sock in 1962 on using chemical information as an aid to structure solution and doing this with what she would call high-speed computing. And it's got this fantastic quote in it where she says, a small machine and an intelligent operator may obtain in 1 hour a result with the use of a sophisticated program a powerful machine could give in 5 minutes. The former may be more desirable if a small machine is readily available, the latter if the problem is urgent and brains are scarcer than money. There was a snag, though, with Pegasus. So by the mid-1970s, when I was doing my PhD, Judith was still using Pegasus. Everybody else was writing programs in Fortran and using the big IBM mainframes that we had at UCL at the time. And Judith's programs, therefore, had to be written essentially in machine code. And so really, she was the only person who could use them or could modify them. And she couldn't pass them on to people in other research groups because they'd moved on into modern high-level languages. So although she could do lots of things quite quickly because she was effectively the sole user of this computer, it did kind of somewhat isolate her, I think, from the mainstream of kind of crystallographic computing. She carried on using it until 1980, after which she went to the Science Museum. It ran there till 2009, but it's now been retired. She did, though, carry on with these methods to some extent. UCL is a hotbed of Bayesian statistics. Our statistics department is frowned upon by some other departments. And Judith was very interested in, again, how much chemical information could you combine and use in solving your crystallographic problem, in solving your structure. And she did quite a lot of work with a chap called Ian Webb in the stats department. And I seem to remember her saying to me that with the methods they'd come up with, you could solve the structure of anthracene from 3 reflections. So you didn't need to measure anything else. But this slide also illustrates another aspect of Judith's character, which is both of these articles are published in Acta Christ, but they're both single pages because they're meeting abstracts. Judith really, she was not keen on writing papers. She liked going to meetings, she liked presenting her work, she liked talking to people, but actually writing the thing up as a formal scientific publication, she wasn't really ever that keen on, at least in the time I knew her. And she was aware of this as something of a failing, and I remember her saying to me that Kathleen was always telling me, Judy, you must publish this stuff, but she said I never really took very much notice. So I'm not the right person to talk about her work on diamonds, and it doesn't just involve X-ray work, but I'll whip through it very quickly. She worked on diamonds for over 65 years, I think. From her PhD right until 2014. She published at least 45 papers as author and co-author on diamonds. She had 10 in Nature, including several front covers. I tried to get the front covers, but I wasn't for the meeting, but I wasn't able to get them. And one really important thing she did was she established a major collection, which we still have, of diamonds from different mines in different parts of the world. And the reason this is really important is that the diamond companies, De Beers and the other companies, they will now not tell you where the diamonds you're buying come from. They amalgamate them all because they don't want people to have a preference for diamonds from a particular location. So it's almost impossible to get this information now. She used X-ray diffraction, and then later on things like cathodoluminescence, infrared spectrometry, mass spectrometry, and so on. The important things I think she did was she looked at nitrogen in diamonds. There's more than one type of diamonds. Type 1 diamonds, almost about 0.1% nitrogen. Type 2 diamonds have almost no nitrogen in them. And their optical properties of those two types are very different. Type 2 are infrared transparent, for example. Type 1 aren't. And that work lasted for many, many years, right through from the 1960s to the 1990s. Using initially X-ray diffraction and then later Fourier transform infrared spectrometry, with which Monica was involved, and Monica helped her a great deal with that. She also worked on inclusions, and strangely Mike mentioned this in his talk this morning. If you measure the cell parameter of a garnet that's been included in a diamond, and then you smash the diamond open and remeasure its cell parameter, it will have increased slightly, because the garnet is under compression within the diamond. And from this remnant pressure, with some assumptions, you can back out the pressure conditions under which the diamond must have formed. And her final really important work on diamonds concerns isotopic composition. She did a lot of work with Colin Pillinger, who was a mass spectrometrist, and they published many papers, several papers in Nature about this, looking at the delta C13, for example, variation between different types of diamond, which can give information about where the diamond formed, perhaps, and under what conditions. Because this is still things that is not that well really understood. This is Judith's last publication from 2014. Very, very unusual stone, which about 1.5 millimeters, 2 millimeters across, which I mislaid for some time. That caused them to be quite cross with me. It contains sort of iron carbide inclusions, and they're looking at the effect on the fractionation of the carbon isotopes between the diamond itself and the iron carbide inclusion in there. So just a couple of slides to finish with. Teaching, she was very keen on teaching, and following on from Kathleen, she ran really excellent courses, practical courses, for initially the chemists and later the geologists on X-ray diffraction. We used to use those S25 oscillation cameras. The students would take their own photos, they would interpret them, and they were really, really good at teaching people the basics of crystallography. Sadly, I doubt it would be possible to teach them in the same way now. We probably couldn't afford it, and we'd need so many demonstrators for it that I don't think we'd be able to do that. She had many PhD students. I think the two most distinguished are probably Josh Thomas, who I suspect she took over from Kathleen when he finished, who was professor of chemistry at Uppsala, and Richard Welbury, who had a very distinguished career at the Australian National University, looking at disorder. And I just wanted to finish with, which I think is really quite important, which is Judith's influence on what is now the Department of Earth Sciences at UCL. When she joined the Geology department, as it then was, in 1978, it was a very small department. It had quite an active micropaleontology research group, but other than that, it didn't really do research. It nearly got closed in 1983 when the University of London reorganised teaching of geology, but it was decided, probably because there were some bright things there, like Judith, that they would keep the department at UCL open and perhaps dispense with the department at Queen Mary College instead. And as a result of that, the three major, what are now major research groups came into being. We have a very good group in high pressure petrology in what's called the Haskell Laboratory. The funding for that fell through in the 1980s, and Judith, by using her contacts, was able to get from her friends high pressure apparatus, load frames and pressure cells that they weren't using. And without that, that lab would not have been set up at all. The fission track analysis group, or thermochronology group, I've spoken to Tony Herford, who was the head of the group for many years, and he said without Judith's help, guidance and influence, that group just would not exist today. It wouldn't be there. And another group, which is one of the great things about our department, I think, is the computational mineral physics group, which is essentially set up by David Price, who came there as a Royal Society fellow in 1983. And I asked David about Judith. Did he know her before he came to UCL? And he said no. He said, but he was always very helpful to him. And I think this is a lovely quote to finish. She was a sharp mind and a good friend to those who passed her high threshold of approval. And that's Judith. Except that I do have one thing that nobody else has. I have some atoms from her here. Because after she died, Monica, her great friend, arranged for some of her cremation ashes, the carbonaceous part, to be turned into a diamond. It's just under 1 carat, so you're going to have to be very careful. You can come and look at it, but Monica's going to keep hold of it, I think, to make sure it doesn't disappear. But I'm sure you're all very honest folk. But anyway, there we go.
Make sure we don't lose it.
Yeah. Rather nice blue colour.
Okay, Ian, it was interesting what you were saying about the fact that she didn't like to write papers, because I was constantly pressing her to write down what she knew about the Kathleen Lonsdale collection. And she was extremely happy to turn up at the collection and talk endlessly about them. But when I said, well, this is all very well, but could you write this down? And it never happened. So I understand entirely that. Okay, any questions? Come on, let's have a couple of questions for you.
All right, time to go home and have our...
I think everybody's getting a bit tired and wanting to go home.
Indeed.
Okay, fair enough. Thank you very much for your... Beyond the podium here. I'm supposed to give some kind of final remark. I suppose one is probably expected to give some incredible words of wisdom, creating a synthesis of everything we've heard today. But since I think we've been here a very long time, and we all want to go home, I would just say 2 things. Firstly, thank you very much to all our speakers for their wonderful talk, which have been most interesting and shed new light on the history of crystallography in Britain, a field in which Britain had great strength. And thank you all for coming along and listening to it. We appreciate it very much. So thank you very much to everybody. Have a good journey and goodbye.